This is the third video for A-level proof, and in this video we're going to look at one of the most complicated proofs that you can do at A-level, which is proof by contradiction. But before we start that, we need to discuss what's called a negation. Now, all proof by contradiction start with you negating a statement. So there's a couple on the booklet for you. So the first one is there are infinitely many prime numbers. So the negation of that statement, okay, is there are a finite number of prime numbers. Okay, so that's the first one. So the statement there are infinitely many prime numbers, the negation of that, there are a finite number of prime numbers. Now the second one starts with the word all. So the statement all popes are Catholic is the statement. So the negation of that is not there are no popes that are Catholic, which you might think. The negation of that statement is there is at least one pope that is not Catholic. Okay, so that's the negation of something that says all. Okay, now the third one you can see is a statement that says something like, if it's raining, then my garden is wet. Now, these statements are in a certain form. If this, then that. So I can write, and I'll write it underneath in red. So this statement is in the form, if A, then B. Now, you might think the negation of that is if not A, then not B. But that's not quite what it is. So let's have a little look. So the statement, if it's raining, then my garden is wet. The negation of that statement is if it is raining, sorry, my spelling, just rub that out and start again. Okay. If it's raining, then my garden is not wet. So you've got to be careful with this, if this then this statements. So again, so the negation of if A then B is if A then not B. So you keep the first one the same and you change the second one. Okay, so that's the usually three types of negation statement that you need to come across when you're doing proof by contradiction. So the first one, there you are, there are infinitely many prime numbers, so there are a finite number of prime numbers. The second one, all, the negation of something that says all. Okay, so you've got there is at least one that's not that. Okay, not all of them aren't, but there's at least one that isn't. And the third one is this, if it's A, then B, the negation of that, if it's A, then not B. So we're going to have a little look at this proof here. Okay, this is in your booklet, and this is example 7. So it says, proof by contradiction that if n squared is even, then n must be even. Now you can see that this is an example of the one that we've just done. Okay, this is an example of the one that we've just done. So that is your A, and this is your B. Okay, so that's your A and that's your B. So the first thing we have to do is we have to do a negation statement. So the negation statement, okay, so we say the negation, and you don't have to write the word negation, but if n squared is even, so we keep the first statement, then n must be odd. Now, therefore, that is what we assume is true. Now, if we can use our algebraic skills to contradict that statement, then the negation we've made must not be true, and therefore the original statement must be true. Okay, so if n squared is even, then n must be odd. Okay, so we're going to start with n equals an odd number. So I'm going to write it as 2k plus 1. You can have any, remember what we talked about when we were doing proof by deduction, you can have any odd number. So you could have 2k minus 1, you could have 2k plus 3, you could use a different letter than k. I've just decided to use k. But I'm going to declare that where k is an integer, okay, an odd number, but we need to make sure it is an odd number. If k was a third, it certainly wouldn't be an odd number, it would be a fraction. Okay, so we're going to start with that statement. Okay, so we've got n equals 2k plus 1. So what we're going to do, we're going to square both sides. So therefore, n squared equals 2k plus 1 all squared. We're going to multiply that out. Therefore, from that, we get n squared equals 4k squared plus 4k plus 1. Okay. Right. Now, if you look at that n squared, you can see, and I'll just and remember what we did when we were doing proof by deduction. N squared therefore equals, okay, that's 2 lots of 2k squared plus 2k plus 1. Okay, now, if you look at that, and I'll just underline it in a different colour, this, based on the statements we've made, is odd. Remember our proof by deduction, right? So the right-hand side is in the form 2p plus 1. Now you know that that is odd. Okay, therefore we've got n squared is odd because 2p plus 1 is in the form of an odd number. But that's a contradiction because we've said if n squared is even, then n must be odd. But we started with an odd and we've got an odd for n squared. Okay, therefore this is what we've got. We've got an even, which we said here, right, does not equal an odd, right, because we said at the beginning that n squared was even. If n squared is even, then n must be odd. We've got n squared being an odd, right, so that's a contradiction. Therefore, that's a contradiction to our negation statement. Therefore, the original statement must be true. Okay, so our negation statement is not true. Therefore, if n squared is even, okay, n, okay, must be even. Okay, right. So that's the first one. Okay, so that's using that that last condition where we produce that negation. Now, we're going to go through two of the most important proofs that you could have for contradiction. So let's have a little look at this example 8. And this one is quite a well-known proof, and it's one that examiners do like or are very similar. Okay, so it says, prove by contradiction that root 2 is irrational. So my negation is I'm going to assume that root 2 is rational. Okay, now remember what a rational number is. So therefore, there exists integers A and B with no common factor, okay, such that root 2 equals A over B. Remember, A can't equal B. Okay? So we're saying there that I can represent root 2 as a simplified fraction, because all rational numbers can be represented as a simplified fraction. So that's my negation statement. So I'm going to start with that piece of information. So therefore, that statement that I've just made, root 2 equals A over B. Now, if I square both sides, I get 2 equals A squared over B squared. Okay. If I multiply both sides by B squared, I get 2 equals, sorry, my apologies. So 2B squared equals A squared. Okay. Therefore, A squared is a multiple of 2. Therefore, A squared is even. Okay? And if A squared is even, then A is even. Now, think about that one. If, so 4 squared is 16, therefore 4 is even. Okay, so any even number squared is an even number. Right, so we're just going to go a bit further now. So we've got that. Now, if A is even, I'm basing this on this statement here, A is even, then, therefore, I can represent A as 2 times K, where K, of course, is an integer. All right, I can represent, remember from this statement here, that A is even, because A squared was even, then I can write A as 2K. Now, what I'm going to then do is I'm going to substitute, and I'll just show you, that into that line above where we said 2B squared equals A squared. So if I substitute that into there, I'm going to get 2B squared equals 2K all squared. If I expand that, I get 2B squared equals 4K squared. Therefore, B squared equals 2K squared. Therefore, B squared is a multiple of 2. Same process, therefore b squared is even, and as before, therefore b, oops, it's a, b is even. Oh, hang on a minute. Now, there's, hopefully you can see now the contradiction. Right, but if a and b are both even, they have a common factor 2. Now, if you look back at the beginning, when I was making my negation statement, I said there exists integers a and b with no, I should say no, common factor. So I've made a contradiction. I've actually contradicted myself. Okay. Which contradicts the assumption, because the assumption is your negation statement. Therefore, the negation statement must be incorrect, and therefore the original statement must be correct. Therefore, root 2 is irrational. Okay. So hopefully you're okay with that. Now, the last one we're going to look at, again, is quite a commonly occurring proof, and it's the proof, we're going to prove by contradiction that there are an infinite number of prime numbers. Okay. So the first thing we're going to do is we're going to assume that the negation is true. All right, and you saw from the grid what the negation is going to be. So we are going to assume there are a finite. Now, again, just remember what finite means. That means that there's a closed list. There's only so many prime numbers in the world. So a finite amount of prime numbers. Okay. So, for instance, okay. So, for instance, we know that 2, 3, 5, 7, 11, 13, all the way up to the last one, which I'm going to call Pn. All right. So, therefore, P1 equals 2, P2 is 3, P3 would be 5. And this Pn, okay, is the last one in the list. Now, I'm going to say let n equal, or be, right, the product of these primes plus 1. So I remember product is multiplying them all together. So therefore, n equals, and it's 2 times 3 times 5 times 7 times 11 times all the way up to times in by Pn plus 1. Okay. Now, this is a process. So, n is not divisible by 2. Okay, because if I divided n by 2, this is what would happen. Now, you don't need to explain this in the proof, but if I divided this by 2, if you remember, your quotient would be, it would go in 3 times 5 times 7 times 11 all the way up to times by Pn times plus 1. Okay, so if I divided this number n by 2, I would have a remainder of 1. Okay, I'll just put since the remainder. Since remainder equals 1. Therefore, 2 is not a factor of n. Right, so this also applies to all the other primes up to Pn. So again, if you divided by 3, you would get your quotient, okay, would be 2 times 5 times 7 times 11 all the way up to times by Pn, and then you would have a remainder of 1. Okay. Right, so none of the known primes are factors of n, therefore n must be prime. Now, we've found this new prime number that wasn't in my original finite list. So this contradicts the assumption therefore the original statement must be true. Okay, so the number of primes is infinite. That's what we were trying to prove was not happening, so I'll just put my apologies. Is infinite. So there are an infinite amount of prime numbers. Now, there are a couple of proofs for you to have a go at, proof by contradiction, and again, we will give you the solutions to those in due course.